we will look into now nth order diffraction. So far we looked at A, B, like you had surface atoms, then one layer below surface atoms. But there could be further more, right? So in general, you see nth order diffraction from HKL, again HKL we are using, it is the plane. We discussed in the last lecture, HKL defines plane. With spacing d dash may be considered as a first order diffraction from NH, NK, NL with spacing d as d dash over n. What does that mean? So let us look at the left one. So you have 1 0 0 plane, okay. So you have 1 0 0 plane. You see here ABC is your path difference, right, that will be 2d sin theta. So if you have to write the Bragg's law for this, what will be that? 2d sin theta, okay. Now see, it is important to see, let us see, 2d sin theta equals to 2 lambda, where n equals to 2 here, okay. Now consider there is another plane. Now we are talking about 2 0 0 planes, okay. You can review the last lecture where we talk about these different planes, what is the difference 1 0 0, 2 0 0 basically, So this is a plane 2 0 0. Now we talk about the 1n, ray 1 and 3, right. Now if there has to be a constructive, if to get the diffraction, so now the spacing is d by 2 here, right. If this is d by 2, right, that is how you got this plane 2 0 0. So now 2d sin theta, 2d by 2 sin theta equals to 1 lambda, right. So see, overall what you are saying here, d sin theta equals to lambda, right, same thing here, d sin theta equals to lambda. The thing is, like, if you write, suppose, so this is the second order for this plane. If you can ask, okay, it can be 1. If it is 1, then here it will be destructive, because then it will be lambda by 2, right. Suppose this is 1, then here it will be lambda by 2, then that means there won't be any constructive diffraction. It's clear. So what can we see from here? So this is the first order, right. So what is written here? So in general, nth order diffraction from HKL, nth order from HKL with spacing d dash may be considered as first order diffraction from NH, NK, NL. So first order diffraction from 2 0 0, right, is equivalent to second order diffraction, okay, from HKL. Second order diffraction from 1 0 0 plane is equivalent to first order diffraction from 2 0 0 plane. Is it clear? Okay. So far we are talking about in one dimension, but in real life you will have the diffraction will occur in all 3 dimensions, right. Bragg's law simplifies it, but if you have to write more general equations, the Laue's equations can be used, right. So crystals are in general 3-dimensional entities. The Laue's equations emphasize the 3-dimensional nature of diffraction. So again, you can, how do we write it? Idea is same, So these are the scatters atoms, right, in one dimension, right. You have incident beam and diffracted beam, right. All you have to do is calculate the path difference. So here you see, and suppose in one dimension you have this spacing between these atoms is A. Same thing you can consider in B direction, you have B, Y direction B, Z direction you have C, A, B, C, think of the crystal. So in just to simplify, we are saying let us look at the one dimension A, where the distance between atoms is a. So, a times cos alpha minus cos alpha 0, that will be the difference, path difference. Okay? Cos alpha minus alpha 0 has to be equal to h lambda if the diffraction has to satisfy, diffraction condition has to be satisfied in that particular direction. Okay? You can calculate this same principle, you can calculate the power difference, right. In this case the situation is a little bit different, right. So, you have a here and it is just good exercise just to see if you are seeing the same thing. So, it can be written as a cos alpha minus cos alpha 0 h lambda. Similar thing can be written in other direction, cos beta minus cos beta 0 k lambda. Same thing can be written in. These are the general equations written in 3 dimensions. So, all have to be satisfied if you want to see the diffraction, right, where h, k and l are integers obviously, because we are talking about the path difference. This is just to highlight the 3-dimensional nature, but just for simplification Bragg's law is easy, it gives you x scalar quantity. Okay. So, in the last lecture we talked about the reciprocal space, right. Only reason we are talking about reciprocal space is it helps you visualize things. This is an entirely different topic, it does not have to have a relation with X-ray diffraction, only reason is it helps you identify the diffraction planes. So, again here what you see in the direct space, you have these arrangement of atoms, right, you have incident beam S0 and diffracted beams S, right. And here suppose you have, these are the lattice parameters, A1 is 2 angstrom, A2 is 1 angstrom, A3 is 3 angstrom. Okay. A1 is in this direction, A1, A2 and A3 comes out of plane. This is the direct space, this is just arrangement of atoms. We are talking about now a plane, this plane where you have this plane where you have incident beam S0, diffracted beam S. Okay, and you know that angle between diffracted beam and transmitted beam is 2 theta, because this is theta, right. Now, in the reciprocal space, how do we construct reciprocal space? Again the same principle, you know, in reciprocal space, suppose you have to write B1, B1 will be A2 cross A3 over A1 dot, right. Same thing you can, so you can try that, you will find that B1 is 0.5 angstrom, 1 over angstrom, you know, angstrom inverse, right. And now, so you have this B1 in this direction, why B1? Because B1 has to be perpendicular to A2 and A3, use the right hand rule, right, you will, this is the B1 in this direction, B2 in this direction, okay. This is the reciprocal space. Now, in reciprocal space, what we do, the rays are usually parallel in direct and reciprocal spaces. So, S0 is here, right, incident ray, you have a parallel, you draw a parallel ray, but the length will be S0 over lambda, that will be, because we are talking about the reciprocal space. So, 1 over lambda, right. So, you start here, you go parallel to S0 and you stop at this point, okay. Now, if you construct this sphere, right, this is the center, right, this is the center, construct this sphere, if it cuts at some particular points, that is the diffraction plane. So, that tells you that at that point Bragg's law is satisfied. So, it is cutting here 1 0 0. So, you see this is the 1 0 0 plane, right. So, wherever it cuts, that means at that location the Bragg's law is satisfied. We will come back to it again in the next slide, why it is so. And also you see that like 1 0 0 is here, right, this is your diffracted beam. Again you see it is parallel to your diffracted beam in direct space. So, the incident and diffracted beams are parallel, like incident beam is in reciprocal space is parallel to incident beam in direct space. Incident beam, the diffracted beam in reciprocal space is parallel to in diffracted beam in direct space. Okay. Now, so you know now, okay, 1 0 0. Now what you can do, you can, so this is basically the origin of your reciprocal space where you ended this one, and now we can construct a limiting. So what we can do, we can rotate this sphere, and you will find another sphere. This is called a limiting sphere. This cannot go beyond that. So you can rotate this sphere, right? You can move this sphere around this. So you will get this limiting sphere that tells you, okay, these planes which are outside, no diffraction can occur. Only diffraction will occur which the points which lie, and where this sphere cuts, like you have to see that where Ewald sphere, this is called Ewald sphere, right, where it cuts those points. Those are the points where the Bragg's law is satisfied. Okay. So, I think you will appreciate more here when we, so reciprocal sphere, we are talking about this Ewald sphere, right. Again it is just to visualize the planes, because from here now you can see, okay, these are, if you have to answer the question like which are the planes which will give you diffraction, you can just tell from here, these are the planes which will not give you diffraction, these are the planes which will give you refraction, if you can construct the reciprocal space. So, it is easier to visualize, and you have this periodicity, you see the periodicity tells about the crystal structure.
How to draw the
yeah. Okay. So, let us talk about this, then I think things will be clarified. We saw that Ewald sphere, like if you have a point on Ewald sphere, you will meet the Bragg's condition. So, think of it as this. So, you have incident ray coming this way, okay, and this is the diffracted beam, diffracted ray, okay, and we are talking about the reciprocal space. So, length is 1 by lambda, okay, 1 by lambda. Now, okay, so this distance is 1 over d. We talked about yesterday, right, in reciprocal space your h, if you the point on reciprocal space, the distance of that point from the origin will be reciprocal of the d in normal plane, like, so this is 1 over d. So, this you can write as 1 over half of it, right, this is 1 over 2d. Is it clear? Because it is half. Now, if you have to write a condition, this is the sin theta. So, but you can write sin theta equals to 1 over 2d over, yeah, this is your sphere, right, we are talking about. So, this length will be equal to this length, right, by lambda. So, what do you see here? If you solve it, you will get, so sin theta equals to lambda over 2d. I am just solving it. So, basically it is nothing but 2d sin theta equals to lambda. So, what mean to say is, see, this is your sphere, it is the reciprocal space, we are talking about the reciprocal space. So, now it tells you if you have a point on the reciprocal space, at that point your Bragg's condition will be satisfied. You can see from this geometry, right. So, this is 1 by lambda, this is 1 by lambda. Okay. And this is the reciprocal lattice origin. So, now we come back to again this. So, how do we construct this? So, first of all, the incident beam in reciprocal space is parallel to incident beam in direct space, right. So, you start parallel to this, and then the length, we are talking about the reciprocal space. So, the length will be, as you have to, the S0 by lambda will be the length, okay. So, where this meets, this is your origin in reciprocal space, right. Now, considering this as a center, you can draw this sphere that will cut, if there is a diffraction here for 1 0 0 plane, it will cut, and this vector which you can find by joining this line. So, this one will be your diffracted beam, because this is again parallel to this, like right. Now, we also want to know other diffraction plane, right. So far we focused on only one plane, but there will be diffraction from other planes. How do we get that? So, now considering this origin, now you have to rotate this sphere. Think of it as rotating, then you will get a limiting sphere, right. That is the limiting sphere, this is the limiting sphere. So, this will tell you that all diffraction plane are contained in this space, right. And how do you find particular planes? When you rotate the Ewald sphere, see where it is cutting. If it is cutting, that point is on that sphere, that means at that point Bragg's law is satisfied because of this, right. If it is on the sphere, then you see that the Bragg's law is satisfied. So, basically idea of reciprocal is just to visualize these planes, right, helps you visualize, right. Otherwise, it is I mean that is a separately different thing, but it just helps you visualize the planes and diffraction. Also you see the patterns, right, you can see the periodicity. Okay. Now, the question comes, you know the diffraction, about the diffraction, Bragg's law has to be satisfied. What determines the possible diffractions, possible directions of diffraction? Now, the question comes, what angle, right. So, for that a general relation is needed to predict the diffraction angle for any set of planes. Suppose for any set of plane we want to calculate what are the directions. So, let us try that for cubic crystal. We know from the Bragg's law lambda equals to 2d sin theta, okay. Now, we discussed in the last lecture the interplanar spacing. You have planes at, there is a spacing between the planes, right, and this is for the cubic system. What you see? Now, you combine these two equations, what do you get? Sin square theta equals to lambda square h square k square l square over 4a square. So, now you know the particular, if you know the HKL plane, suppose you know a plane, you know the lambda, and you have a particular crystal structure like suppose a cubic system, you can find out all the thetas where you will have a diffraction. So, this relationship can be used to predict the angles, the diffraction directions, because not at all direction you will get diffraction. See, this relationship will change if the system is different. I am just giving an example for the cubic system, because this relationship will be different for tetragonal system, for an example. But this relates, right, the theta and your plane HKL, because that is the second question comes to the mind, right. Now, we want to know which are the planes, like if you know the planes, what are the angles we will get diffractions, okay. And there are different ways of here in this you see the methods. How do we do these diffraction experiments? So, Laue method, basically what you do, lambda is varied, theta is fixed. You have to vary one thing, right. So, either you can vary lambda, so in this case theta is fixed. Rotating crystal method, you have fixed lambda, lambda is fixed, you are varying theta. powder method you have fixed lambda, theta is variable. Okay, these are just methods, like how do we do this diffraction. Okay, I think we will pick it up from here, but the in the next lecture what we will see. So far we know about the diffraction, we know where the Bragg's law is satisfied. Now the question comes, what happens to the intensity, because eventually we want to get a pattern. X-ray diffraction, we want to get a pattern, and pattern means, obvious question is, we want the location. First of all, we can get the location, the positions. Sin theta, the last slide we discussed that how can we relate, like if you know the HKL plane, we will know the theta where you get the diffraction. Now the question is, what will be the intensity? So that is the question we will answer in the next lecture. We will look into the intensity of diffracted beams. What are the factors which influence the intensity? Okay.